Welcome back, everybody. This is our first video in NEET previous year questions for chapter Nuclei of the class 12th. Before this, we have covered several chapters for class 11 and 12th, and all of those are available in our playlist sections on the YouTube channel. So you can go to channel and find those videos. If you find these videos useful, helpful, then do press the like button, share them, subscribe to our channel. Want to support us financially, scan the QR code in front of your screen. With this, let's start today's video. So here, first question, the nuclei of which of the following pair of nuclei are isotopes? So we have to find out isotopes. Now, in isotope, basically, what is the basic definition for isotope? That they have same number of electron or protons. So basically their atomic number will be same. Now here this is 74 is the mass number, 34 is the atomic number. So for option A and B, atomic number is not same. In option A, atomic number are not so same. Oh, sorry, we have to find out isotones. So isotope we discussed. What is isotones? Isotones are the elements where we have same number of neutrons. So how you will find neutron? We will subtract atomic number from the mass number. So for the first case, for option A, number of neutrons for the first are 40, 74 minus 34. And for the second one, these are also 40. For second, 84 minus 38, this will give us for 36. And for the second one, we will get 40, 38. So these their number of neutrons are not same. So option B is rejected. Going to option C, similarly, you will find in the first one we have 50 and in the second one we have 52. So that's why this is also rejected. Similarly, option D is also rejected. So here only option A is the right answer. Now a nucleus represented by the symbol AXZ. So this A is mass number, and it is basically a combination of proton plus neutrons, and this Z is atomic number, and atomic number is basically number of protons. Sometime you will confuse that this may be equal to number of electrons, but actually this is number of protons. Sometime there may be some charged particle which have the less electrons. Let us, for example, this is our helium atom. Its atomic number, its mass number is 4 because it has 2 proton and 2 neutron, and its atomic number is 2 because it has 2 electron. Now if I strip one of its electron, then it will become 4He, 2 positive. Its atomic number is still 2, but it has now only 1 electron. So this 2 actually indicates number of proton, not number of electrons. Number of electrons will be calculated using the amount of charge it has and number of proton it has. We will subtract this positive charge from this number of proton and we will get number of electrons. So here Z denotes proton and A minus Z denotes neutron. So option B is the right answer. In the nuclei of sodium, the number of proton, neutron and electron. So this is basically 2311. So here proton are 11. This is neutral, so electrons are also 11, and number of neutrons will be 23 minus 11, that will be 12. So protons 11, neutron 12 and electron 11. So 11, 12, 11. I think there is some problem in the state answer. There will be some typing error. So it should be like this: 11, 12, 11. In the next one, A nucleus of mass number 189 splits into two nuclei having mass number 125 and 64. The ratio of radius of the two daughter nuclei respectively. Now, in case of a nuclei, let's first discuss for hydrogen-like atom. For hydrogen-like atoms, we discussed that Rn was basically n square into R node, where R node was 0.529 angstrom. This is for hydrogen-like elements. Now we are discussing regarding nucleus. So in case of nucleus, radius of the nucleus is basically equal to R node, that is the base radius, into A raised to power 1 by 3, and this A is atomic mass, and R node is constant, that is 1.2 Fermi. So now radius for first nucleus, so radius for 120 nucleus with 125 mass number will be equal to R node 125 raised to power 1 by 3, and radius for nuclei with atomic mass 64 will be R node into 64 raised to power 1 by 3. So their ratio of R125 by R64 will be equal to 5 by 4, and that is option C for us. Let us move ahead. If the nucleus 2713 aluminium has a nuclear radius about 3.6 Fermi, then for this one would have the radius approximately. So we have already discussed the formula that R A will be equal to R node into A raised to power 1 by 3. Now for aluminium, this is 3.6 Fermi is equal to R node is not given, so we will keep it as it is, and its mass is 27 and raised to power 1 by 3. Now for this one, tellurium, it will be, let's say radius is RT, and that will be R node into 125 raised to power 1 by 3. So what we will get from this, if we divide both of these, we will 3.6 divided by RT is equal to 27 raised to power 1 by 3 is 3, and 125 raised to power 1 by 3 is 5. So this will cancel on 1.2, and RT is basically 6 for me. That is option D for us. Now the next one, if the nucleus 27 aluminium is 3.6 Fermi, approximate radius of 64 copper. So again, 3.6 is equal to R node 27 raised to power 1 by 3, and for copper, let us say R is equal to R node 64 raised to power 1 by 3. Divide these two, we will get 3.6 by R is equal to 3 by 4. This will go on 1.2, and from this R is basically 1.8 Fermi. Oh, sorry, 4.8 Fermi. 1.8 Fermi. That is option C. Let's move ahead. Two nuclei have mass number in ratio 1:3, ratio of their nuclear densities. Now, we have already discussed it many times that nuclear density is constant. So if nuclear density is constant, means its ratio will be 1:1. That is option D for me. Now the next one, the ratio of germanium nuclei is to be measured to the twice the radius of 9 by 4 beryllium, the number of nucleons in germanium are. So it is mentioned that radius of germanium is equal to twice the radius of beryllium. So radius of germanium will be equal to R node into number of nucleons in germanium. So let's say that is AGE, and raised to power 1 by 3 will be equal to twice R node. Now for beryllium, it is 9 and raised to power 1 by 3. So what we can cancel R node, and if we take cube of both of these sides, we will get AGE is equal to 8 times 9, that is basically 72. So option A is the right answer here. In the next one, the volume occupied by the atom greater than the volume of the nucleus, about the factor. So for this, what we need to know? We need to know the radius of both nucleus and a normal standard atom. So radius of nucleus is about 10 raised to power minus 15 meter, and radius of an atom is about 10 raised to power minus 10 meter. So these are the basic ranges of radiuses. Now, so volume of atom divided by volume of nucleus will be equal to 4 by 3 pi volume of atom, that is 10 raised to power minus 10 cube, divided by 4 by 3 pi volume of nucleus, that is 10 raised to power minus 15 cube. And from this we will get 10 raised to power minus 5 additional, that will give us 10 raised to power 15, a factor of 10 raised to power 15. So option D is the right answer. In the next one, a nucleus with mass number 240 breaks into two fragments, each of mass number 120. Binding energy per nucleon of unfragmented nuclei is 7.6 MeV, while that of fragmented is 8.5 MeV. The total gain in the binding energy in process. Now, in the question, we can see that binding energy of unfragmented nuclei is 7.6, while the of the fragments is 8.5. Means here, daughter nucleus or daughter nuclei are more stable than parent. Okay. So now, to find out the total gain in binding energy, what we can do? That delta E, that is the gain, that will be equal to we have that will be equal to total energy of daughter nuclei minus total energy of parent nuclei. Now, in terms of daughter nuclei, we have two fragments, each of 120. So twice 120 into 8.5, that is their binding energy, minus 4 parent, that will be 240, multiply 7.6. So this will be basically 240 multiply 8.5 minus 7.6, and this will lead to something around 216 MeV. And these are in MeV. Now total gain in binding energy. So what is binding energy? Binding energy is basically delta E by the total number of nucleons. So we have gained total energy of 260 by total of total number of nucleons are 240. It's actually 2 into 120. So this will give us 0.9 MeV per nucleon. So this is the amount of energy we have gained in the process. And so option A is the right answer. And from where we gain this energy has to be provided from the outside. Oh, sorry, not provided from the outside. It has to be come from the mass difference. What is that? Yeah, it has to be comes from the mass difference. It's basically a nuclear fusion process. Nuclear fission process. Now let's move to ahead. The energy equivalent of 0.5 gram of a substance is. So we have to convert 0.5 gram into energy. Now from the Einstein relation, we know E is equal to mc square. So mass is here 0.5 grams, so 0.5 into 10 raised to power 3 into c square, that is 3 into 10 raised to power 8 whole square, and this will give us 4.5 into 10 raised to power 13 joule. So option A is right answer. Binding energy per nucleon of lithium helium nuclei are given. In the nuclear process, lithium plus hydrogen give us helium plus Q. The value of energy released is. So if we see here carefully that binding energy per nucleon of lithium is smaller and binding energy of helium per nucleon is greater. So the formula for Q value here, that will be Q value, that will be binding energy for daughter, total binding energy of the daughter minus total binding energy of the parent. Now, if you look carefully here, nothing is given regarding hydrogen. That what will be the binding energy of hydrogen. So what we will assume, we will not consider it. So for helium it is given. So Q value will be equal to 2 times. For helium it will be 4 times the binding energy. That is for helium it is 5.6. Yes. Oh, sorry, not 5.6. That is 7.06. And that is for helium. Minus for the parent, that will be for lithium, that is 7 times. Why we had 2 here? Because we had 2 heliums. That's why we added 2 here in multiplication. So 7 times 5.6. So this will give us the Q value of the equation, and that comes out to be around 17.28 MeV. That is option D for us. In the next one, how does binding energy per nucleon vary with the increase in the number of nucleons? So for this, we have a very simple graph which we can use. So suppose this is the axis, x and y axis. Here we have number of nucleons, and here we have binding energy per nucleon. So this graph varies like this. Let me draw a line. So this graph varies like this. First it increases, then it decreases, and then it's just saturates. So binding energy first increases, then decreases. So first increase, then decreases with increase in the mass number. So that is option B. And now this peak here comes from, this peak is for regarding iron, where I think mass number of iron is mass number of iron is around 56 or something, or it may be atomic number, I don't exactly remember. But this is for the peak is for iron. This is the iron has the most stable nucleus. That's why it's found inside the core of stars. Now below iron we have fusion process. Nuclear fusion happens below iron, and nuclear fission happens after iron. Means all the nuclei with atomic number greater than iron will split, and they will come to about to iron, and all the nuclei with atomic number less than iron, they will fuse to form the iron. So that's the basic process. Now with this, let's move ahead. The mass of lithium nucleus is that time less than the sum of masses of its nucleons. The binding energy of nucleus is nearly. So we have been given here mass difference. So from this mass difference, we can calculate the energy difference, or delta E will be equal to delta M times C square. That will be equal to 0.042, and it is in AMU. So if this is given in gram, if delta M is given in gram, then this formula delta MC square give us answer in joules. But if delta M is given in AMU, or atomic mass unit U, then what we will do? We will do number value of this AMU multiply the 931.5. This is the electron volt equivalent. So this will give us around 39.12 MeV. So now we have the energy difference. So we will divide it by the number of nucleons and we will get the binding energy per nucleon. So 39.12 divided by 7 will give us something around 5.5 MeV. So you have to remember this one important thing, that if delta M is given in gram, so we will get answer in joules. But if it is given in AMU, just multiply it by 931.5, because this 931.5 has the unit of MeV by C square. MEV C square AMU. So if we multiply it by here delta M C square, that C square gets cancelled. This unit of this mass AMU, that's get also cancelled, and we are only left with MEV. So that answer will be 5.59. That is option B. Now let's move ahead. If MAZ, MP and Mn denotes the mass of nuclei AZX, masses of proton, neutron respectively in units of U. 1 U is 931.5 MeV per C square. The binding energy represents its binding energy. Binding energy represents binding energy in MeV. So basically we have to find out binding energy in MeV. So that binding energy will be basically total number of protons, that will be equal to Z into mass of one proton, plus total number of neutrons, that will be equal to A minus Z into mass of neutron minus the given mass of that atom into C square. This is the basic formula for binding energy. Now let me explain what does this actually mean. Suppose we have a lithium atom, 7 lithium 3. So if I want to write the same formula for this lithium, then I can write that binding energy for lithium will be equal to 7 times the mass of proton plus 4 times the mass of neutron minus the mass of this atom, that is given to be 7 units into C square. I'm assuming that its mass is 7 unit. So from this I can write that binding energy by C square, and here I will get is equal to ZMP plus A minus ZMN minus M of AZ. So from this, mass AZ will be equal to ZMP plus A minus ZMN minus BE by C square. So that is option A for us. Now in the next one, in nucleus AZ mass represented by MAZ, if MP and M denotes the mass and energy respectively, then we have to find out the formula for binding energy. We just solved it, that it was ZMP plus A minus ZMN minus MAZ into C square. That is option A. Now next one, binding energy of deuteron is 2.2 MeV and that of helium is 28 MeV. If two deuterons are fused to form one helium, the energy released is. So as mentioned here, that we have fused two deuterons. So let us write for deuteron, that will be 2d1. It is basically hydrogen with one additional proton. That's why I'm not writing H. So 2d1, we have fused two deuterons and we have formed a helium atom. Now we have to find out energy released. So how we can find out that delta E, that energy released, will be equal to the total energy of helium atom, total binding energy, that is given to be 28 MeV, minus total binding energy of this parent, so that will be 2 into 2.2. So this will be around 23.6 MeV. So option C. Next one, here we have a reaction in the binding energy of 2H, 3H, 4H are respectively A, B, C, MeV. energy released. So again, energy released will be equal to delta E will be equal to total energy of the daughter minus total energy of the parent. So total energy of daughter. Here neutron is free. This is, we have only one neutron and it will be free. So we will not have any binding energy related to this. We will have only binding energy for helium and it is C. So C minus we will have A plus B. So it will be C minus A minus B. So that is option C for us. Let's move to the next one. MP denotes the mass of proton, Mn denotes mass of neutron. At a given nucleus, binding energy contains Z protons and neutron and mass M and Z of the nucleus is given by, where C is the velocity of light. Now we know that binding energy, and I think this we have solved this question already. Let me find out. Here it is. That mass Az is mzmp plus A minus zmn minus Be c square. So the answer will be in this question, that will be nmn zmp. Here we have number of neutron is given as n, sorry. In the previous one we have taken number of neutron as A minus z. So basically n is equal to A minus z here. So we can say option A is right here. Now in option B, there is slight difference that it is BC square and it should be B by C square. So option A is right answer. To the next one, the energy equivalent of one atomic mass unit is. So we know that here it is mentioned one atomic mass unit. So we know that 1 AMU is basically equal to 931 MeV per C square. So that is option C is the right answer. If we multiply it, the energy equivalent will be 1 AMU into C square. That will give us 931.5 MeV to be exactly. So now next one. Select the correct statement among the following. Slow neutron can cause fission into 235 uranium and then the fast neutron. Yes, that is right answer. Moving to the next, that alpha rays are helium nuclei. So yes, this statement is also right. Now third, beta rays are the fast moving electron or positron. Yeah, that is also right. We have beta negative and beta positive. So here we are taking consideration as journal beta rays. So, and coming to the fourth, gamma rays are EM radiation of wavelength larger than the X rays. So we know that energy of gamma rays is greater than the energy of X-rays. So frequency of gamma rays will be greater than frequency of X-rays, and we know the frequency and wavelength are inversely related. So wavelength for gamma will be smaller than the wavelength of X-rays, which is wrong. So according to which statement 4 is wrong. So 1, 2, and 3 are the right here. So we can say option A is the right answer. Now, water is used as coolant in nuclear reactors because it has a very high specific heat capacity. What does it mean? That it takes lot of heat to raise temperature of water by same degrees as compared to some other liquid. That's why we use water as a coolant, because it can absorb lot of heat and there will be small increase in temperature. With small increase in temperature, it can absorb lot of heat. The next one, when a uranium isotope 235U is bombarded with a neutron, it generates 89 krypton, 3 neutrons, and so we have to find out that what will be the next, what will be the next daughter nuclei. So 235U 92. And bombarded is a neutron, so there will be a addition of neutron. And what we are getting 89 Kr36 plus we are getting 3 neutrons, so 3, 1 and 0 plus. Now we have to compute that what we will get here. So if we balance, then we will get 92 plus 0 should equal to 32 plus Z, and from this Z is 92 minus 36, that will be 6, and here we will get 8 minus 3, that is 5, so 56. And here in given answer there is only one element which has an atomic number as 56, so option D is the right answer here. Now the next one, a certain mass of hydrogen is changed to helium by process of fusion. The mass defect in the fusion reaction is 0.028666 U, energy liberated. So, and delta E will be basically delta mc square. Here we have mass in AMU, so it will be 0.02866 multiplied by 931, and answer will be in MeV, and it will be equal to 26.82 MeV. Now we need energy liberated per U. I think it should be per nucleon. It should be energy liberated per nucleon. There will be some misprinting, some typing error. So energy liberated per nucleon will be equal to 26/82 divided by number of nucleons in the final daughter element, that is helium, and it has a 4 nucleons, so divided by 4, and that will be equal to 6.67 MeV. That is option C for us. Now the power obtained in the reactor using uranium-235 disintegration is 100 kilowatt. The mass decay of uranium-235 per hour is, so here we know that power is 100 kilowatt. So power means joules per second. So we are getting 100 into 10 raised to power 3 joules per second. So let's do calculation for, and we have to find out decay per hour. So this is the energy liberated per joule per second. So energy liberated per hour, or in an hour, that will be 3600 into 100 into 10 raised to power 3, that will be basically 36 into 10 raised to power 57. So we need to generate that much amount of energy in an hour. Now there is one more thing that is not specifically mentioned in the question, that for 235 uranium decay, the energy produced per fission is 200 MeV. So per fission we have 200 MeV energy produced, and that will be equal to 200 into 10 raised to power 6 into, that is in MeV, so 1.6 10 raised to power minus 90. Now it's in joules. So this will give us 3.2 into 10 raised to power minus 13 joule. This is the amount of energy per fission, and we need this amount of energy. So number of fission that we will need, so N will be equal to 36 by 10 raised to power 7 divided by 3.2 10 raised to power minus 30. So we will need 36 by 3.2 into 10 raised to power 20 fissions per hour. Now let us assume that each atom goes to fission. So each atom is going to fission, means we need that number of atoms in an hour to get the required energy output. So let's convert them into let's convert this number of atoms into mass. And how we will do that? We know that 1 mole of uranium-235 has a mass of 235 gram and has 6.022 into 10 raised to power 3 number of atoms. So we can reverse engineer this process. that one atom will have a mass of 235 divided by 6.022 into 10 raised to power 3, and we have number of atoms equal to this value. So total mass will be total mass 253 by 6.022 10 raised to power 23 into we have 36 by 3.2 into 10 raised to power 20. This will be the total mass, and that comes out to be approximately 40 into 10 raised to power minus 6. Oh, sorry, minus 9 kilogram. Okay, correction here, correction. It will be not in kilogram, it will be in grams, and minus 6 grams. Why? Why in grams? Because we took it in grams. While doing calculation, we took it in grams. So basically, the answer is 40 microgram. And it matches with option B here. Option B is the right answer. Let's move to the next one. Fusion reactions take place at high temperature because atoms gets ionized. Kinetic energy is high enough to overcome the Coulomb repulsive. Molecules break up at high temperature. Nuclei break at high temperature. So the right answer is here option B, that kinetic energy is high enough to overcome the Coulombic repulsion between the nuclei. So both of the nuclei come in the close vicinity of each other and then they get fused. And we have fusion reaction. So option B is the right answer. Now, the binding energy per nucleon in deuterium and helium are 1.1 and 7 MeV respectively. When two nuclei fuse to form a helium nucleus, the energy released in the process. So we have already solved this type of question, that we have 2H1 plus 2H1 give rise to 4He2. So the energy released will be equal to delta E. That will be the total energy of the daughter nucleus. That will be 4 times 7 and minus total energy of the parent nucleus. That will be 1 into 1.1 multiplied 2, because we have two similar parent nucleus. And this will give us 23.6 MeV. This is the total energy released, or this will come from the binding energy. If we want binding energy per nucleon, we can divide it by 4. Now coming to the next one. In any fission process, the ratio of mass of fission products, mass of parent products. So here, as mentioned here, that we are having fission reaction. So what we have in fission reaction, energy is produced. So if energy is produced, from where does this energy comes? This comes from the mass defect. So we can say mass of daughter nucleus is less than mass of parent nuclei. So the ratio mass of fission product, means mass of daughter products, divided by mass of parent will be less than 1. So option C is the right answer. Fission of nuclei is possible because of binding energy per nucleon in them increases with mass as mass is low. We have just discussed this type of graph, that suppose if this is a graph where this denotes number of nucleons, or we can say basically atomic mass, and here we have binding energy per nucleon. So this curve shows this type of behavior, and then it saturates, and its peak is at iron. Now on the left side we get fission, in the left side we get fusion, and on the right side we get fission. So the fusion fission, yeah. So fission is only possible. Why? Because as we move backward, or as we move towards the low mass number, then binding energy per nucleon increases. So as we move backward, binding energy per nucleon increases, or we can say with lower mass number, binding energy increases. So here increase with mass number at low mass number. That is option A. So moving to the next one. In a nuclear fusion process, the mass of the fusing nuclei, let be M1 and M2, the mass of the resultant nuclei will be, again, we know that as this is fusion process, so there will be energy released. If energy is released, means there will be mass defect, and if mass defect means mass will be less. So if mass is less, then we can say M3 will be less than the sum of M1 and M2. That is option C. In the next one, solar energy is mainly caused due to fusion of proton during synthesis of heavier heavier element. Now, this is what happens inside the sun. That sun has lot of hydrogen. So what it does, it fuses hydrogen to produce helium. Then it fuses helium and helium hydrogen further to produce elements like carbon, oxygen, and these kind of elements. Then further it moves to silicon, and further in final it moves to iron. So the process stops at here. At the fusion process stops at here, iron. You cannot fuse iron to produce any other element because it has the highest binding energy per nucleon. So the energy produced by the sun is due to this fusion process. In each fusion process, there is loss of some mass, and that mass is that mass loss comes in the form of energy production. So option C is the right answer. Which of the following are suitable for nuclear fusion process? We have fusion, so we need light nuclei. For fission, we need heavier nuclei. Now, nuclear fission can be explained by proton-proton cycle, liquid drop model, independent nuclear particle model, and nuclear shell model. So we can say the easiest explanation comes from the liquid drop model, and how it explains. It's explained by, suppose this is a nucleus represented by a drop. Then what happens due to some unknown variables which is not known? Then the shape of this liquid drop changes to like this dumbbell shape. Now we have this thin section developing here, and soon this section will break, and we will have two individual nucleuses, and this smaller nucleus will go outside as known as alpha decay, sometimes or some other element. So that's the basics of liquid drop model. Coming to the last one. Heavy water is used as a moderator in the nuclear reactor. The function of a moderator is to slow down the neutrons to thermal energies. And why we need to slow down the neutrons? Because fast neutrons can't cause fission with uranium-235. That's why we need slow neutrons, and to slow those neutrons we need heavy water. And why only heavy water? Why we cannot use some other liquid like sodium? Even sodium is used, so mostly heavy water is used. So that you can explain if you have studied collision, or most prominently elastic collision. So in elastic collision, if you have two masses, let's say M1 and M2. Now if M1 is comparable to M2, not exactly comparable. So if M1 is comparable to M2, then what happens? There is highest exchange of energy. Means, suppose this M1 is neutron and this M2 is heavy water. So what happens? Initially this heavy water is at rest. So what happen after collision? That neutron loses most of its energy, and heavy water acquires energy. So due to this energy, this water starts boiling, and when this water boils, we produce steam. Now this steam is used to rotate the turbine or electricity generators, and we get electricity. So that's how we use heavy water to moderate. Now why we cannot use normal water? Now mass of normal water, because what is normal water? H2O. And what is heavy water? That is D2O. Mass of normal water is slightly less than the heavy water, so there is not that much good exchange of energy. That's why we use heavy water. So with this, this video is complete. Hopefully what we have covered is helpful to you. Again, if any doubts or suggestion, put them in comment section. I will like to resolve them. And find these videos useful, helpful, then subscribe to our channel, share this video, and like to donate us something, scan the QR code in front of your screen. Thank you for watching.